Hello and welcome to our paper review presentation. We're from Group 1. Today, our presentation is going to discuss the Computational Fluid Dynamics Assessment of the Effect of Bioprinting Parameters in Extrusion Bioprinting, a research which is originally performed by Rashik Chand, Beni Shimwa Muhire, and Sanjairaj Vijayavenkataraman. In today's presentation, we'll talk about the introduction of the research methods used in the research, and then the results, and then finally we'll talk about the conclusion of the whole research itself. Let's just get into the introduction. So bioprinting has become an integral part of tissue engineering. In tissue engineering, it is used to construct tissues and also organs. Biocompatible structures to replace organs in case of an organ transplant. One of the most popular form of this method is called extrusion-based bioprinting. It is very affordable, simple, and scalable. However, since this method is very similar to 3D printing, where we use nozzles and pressures at the inlet to dispose of the bioink filaments, the nozzle design will greatly affect the cell viability, and the shear stress is linearly affecting the cell viability also. However, since these nozzles are very small, it is very difficult to perform experimental studies to learn about the shear stress and also the shear stress distribution within the nozzle, so that we need an alternative methods of researching these parameters. So what do we do? This is why computational fluid dynamics is very important, since computational fluid dynamics is a branch of fluid mechanics that uses numerical analysis and algorithms to solve fluid flow situations using the help of computers. In our case, what it solves is basically the Navier-Stokes equation, and since it is solving a set of partial differential equations, we can know the distribution of the shear stress, the velocity, the pressure, temperature, etc. And it is used to understand the flow structure, the forces associated with the flow, and also the energy transfer occurring within our control volume. It is important to note, however, that computational fluid dynamics is let's say a good approximation of the real fluid flow situation, where there are some errors associated with this method also, since we're using numerical methods of predicting an otherwise very complex fluid flow and Navier-Stokes equation. In the computational fluid dynamics paradigm, there are several processes to keep in mind. The first one being modeling the geometry using computer-aided design. And then after we've done that, we can export the CAD file into the meshing software, where it is discretized or it is chopped up into multiple degrees of freedoms. After that, we define the physics that we want to apply in our fluid flow case. We can either apply gravity or no gravity. We can apply what sort of turbulence model that we want to use. We can apply the boundary conditions here, the viscosity, etc. And then after that, of course, it solves the Navier-Stokes equation based on the boundary conditions which has been pre-described. And those numerical results is usually post-processed into a velocity, shear, or pressure contour stress, or other kinds of pressure contour stress, in fact. And we can know the distribution and also the maximum value of all those parameters from post-processing. The geometric modeling used in this research focuses on 3 types of nozzles. The first one being a tapered conical nozzle. The second one, a conical or a basic, or not basic, I'm sorry about that, a regular conical nozzle, and the last one being the cylindrical nozzle. All of the inlet diameters has been kept constant for all kinds of nozzle geometry at 10 millimeters, whereas for the conical nozzle geometry, the tapered the the outlet diameter is varied between 0.1, 0.3, and 0.5 millimeters. There are several bioinks that has been considered for this study, coming from 4 different references. However, in the end, the Ink 040 NFC alginate mixture with a viscosity of 100.73 and a density of 998.2 is used. The boundary conditions and spectral discretization are as follows, where the outlet pressure is set at a 0 Pascal gauge pressure, which means that the absolute pressure is still 1 atmospheric pressure. 6 different values were used for the inlet pressure gauge. Also, this is a gauge pressure also. 0.025 megapascal, 0.05 until 0.25 megapascal. So the inlet pressure has been set to be at a minimum of 0.025 above the atmospheric pressure, and at maximum 0.25 megapascals above the atmospheric pressure. The inlet mass flow rate was kept constant at 0.0015 for each case, whereas the substrate movement was modeled as a translationally moving wall at velocity of 0.5 and 10 millimeters per second. A transient case is also simulated in this research, where they use a time step of 0.01 second with a cumulative total flow time of 10 seconds. The pressure velocity coupling was discretized by applying the Piso algorithm, whereas the momentum term was discretized using the second order downwind methods.
Now we will begin to explore what the authors found through their simulations and tests in the results and discussions section. We need to recall that the factors being investigated by the authors are the effects of the nozzle geometry, the nozzle diameter, the inlet pressure being applied, as well as the effects of the bioink rheology being selected and its relation to the printing speed. And so, first, we will see the results on the tests on the influence of nozzle geometry. So, from their simulations, the authors found that across almost all inlet diameter variants, being 0.1, 0.3, and 0.5 millimeters of diameter, as well as through different inlet pressures, the tapered conical nozzle geometry showed the lower maximum wall stress compared to the conical nozzle. But here we also observed that the cylindrical nozzle showed significantly less stress than the two, especially for the 0.1 and 0.3 millimeter diameters. This would generally imply that the cell survivability in cylindrical nozzles should be the lowest, since it provides the least amount of stress compared to the other two types. However, we need to also consider that the cylindrical nozzle has its own share of issues. The first of the two being that the higher overall stress experienced by the fluid as in the walls of the cylindrical nozzle. We can see from the figure 3 here, where we see the stress analysis of the visual simulations of the nozzle types. We see that the section of higher wall shear stress, or we can see from the yellow and red sections, has a longer section in the cylindrical nozzle compared to the other two types. This implies that with this longer segment of higher stress experienced by the fluid, the total overall shear stress experienced by the fluid is higher, even if the maximum amount is lower compared to the other two types. This would imply that the cells in the bioink would experience higher stress for longer periods of time, leading to even lower cell survivability, contrary to what we expected in the first place. The second one being that cylindrical nozzles show a very low mass flow rate of the bioink, so that it shows that in the simulations that even with higher inlet pressure provided, the mass flow rate of the cylindrical nozzle remains the lowest out of the three. This means that even higher inlet pressure is required to provide the same mass flow rate in the cylindrical nozzles compared to the other two nozzle types. When we provide even higher pressure, this would mean greater shear stress and in the end lower cell survivability in the hopes of achieving the same mass flow rate, which is something that is not ideal in the case of bioprinting. Next, we also consider the influence of the nozzle diameter. When we change the diameter of the nozzle, especially when we decrease it, we result in a lower cross-sectional area and we expect an increase in pressure of the fluid being released. In the simulations, a decrease in nozzle diameter generates escalating increase in maximum wall shear stress as we expect. We see from the table 3 that as the pressure increases, which is resultant of the decrease of diameter from 0.5 to 0.1, there is a higher percentage increase in maximum wall shear stress for the tapered conical and the conical nozzle types. But this does not apply to cylindrical nozzles, where we see that the smaller the diameter gets, a higher pressure results in a lower increase in stress, so that for the cylindrical nozzles only, a lower diameter, which usually increases pressure, is better as it decreases the wall shear stress.
Next, we discuss about general influence of inlet pressure. Increasing the inlet pressure raises the mass flow rate of the fluid and at the same time proportionally increase the max wall shear stress experience. If you can see in the figure 6, in the cylindrical nozzle, higher dispensing or inlet pressure, the mass flow rate will increase. This is true for all three nozzle geometries and all nozzle diameter used. As we see in the right figure, where there increase inlet pressure with increase in higher maximum wall shear stress. Higher inlet pressure combined with greater nozzle diameters increase mass flow rate at exponential rate. If you can see in the figure 6, when we use higher diameter of the nozzle, the same increase in dispensing pressure result greater increase in inlet mass flow rate change. Next, we discuss about bioink rheology and shear thinning. Viscous fluid like bioink have a property called shear thinning, where viscosity reduces as shear stress increase. Greater shear thinning is desirable as it prevents nozzle clogging and reducing concentration of shear stress. The four selected bioinks have different power law indexes N that correlate to their shear thinning ability. In all three nozzles, bioinks with lower N value experience less shear stress, meaning N value is inversely proportional to shear thinning ability. The selected bioink with the lowest N, alginate sulfate nanocellulose, with N is 0.0863, experience the least shear stress across all tests, indicating the highest cell viability, like you can see in the figure on the right-hand side. Next, the result of bioink rheology and printing speed. Lower N value in bioinks also correlate to more positive relation between inlet pressure and outlet mass flow rate. For lower N value, better shear thinning, the same increase in inlet pressure result in greater increase of outlet mass flow rate. Using bioinks with better shear thinning reduces the need for higher inlet pressure to reach desired mass flow, reducing shear stresses and improving cell survivability. Now you can see in the figure 9, line graph of outlet mass flow rate against inlet pressure of 4 bioinks.
From the results, the following conclusion has been made. The lowest maximum wall shear stress can be found in the cylindrical nozzle. The maximum wall shear stress, however, is experienced over the entirety of the cylindrical part. For the tapered conical nozzle and the conical nozzle, this is only at the outlet. A tapered conical nozzle has a lower maximum wall shear stress than the conical nozzle. When determining the shear stress, the mass flow rate is crucial. For the cylindrical nozzle, the mass flow rate deteriorated throughout the nozzle, which meant a higher inlet pressure was required, which led to higher shear stress. It also led to a shorter time of the cell being within the nozzle. Increasing the nozzle outlet diameter makes for an increased mass flow and a decreased wall shear stress. The disadvantage is a decrease in resolution. It has not been found in the research that an higher inlet pressure has more negative effects than a decreased outlet diameter on the shear stress. The results within this paper have been made computational fluid dynamics simulation. This shows that it is possible to make a trap profile with these simulations. The simulation itself also showed that the optimal printing speed is independent of the nozzle geometry when you have a constant outlet diameter and a constant mass flow rate. The empirical relationships found with the simulations make it possible to compare bioinks and experimental methods. It is important to realize that all of these conclusions based on parameters are just parameters. The entire system is a whole, which means to totally understand your setup and your optimization, it is important to understand parameters as a whole and apply the conclusions based on the whole system. The fact that it was possible to quantify parameters that are normally not able to be measured in experimental setup, but using computational simulation, makes it possible to optimize bioprinting parameters, develop and compare different bioinks and experimental setup, but it also reduced the number of trial iterations needed within experimental setup to optimize the used bioinks. When the simulations are used efficiently, this will increase the efficiency of the bioprinting processes enormously and also help with development of future approaches. Not everything has been researched within this paper, so possible research options of the future contain a cylindrical nozzle simulation with a constant mass flow rate and not a higher inlet pressure to make sure that the outlet mass flow rate is equal to the other types, but a constant mass flow rate overall. A second option is a 3D simulation of the bioink trap profile under experimental conditions with the simulation of actually involving cells. These simulations up until now only contain bioinks with no cells. A third research option is the experimental verification of the simulation results, to make sure that the simulation results are actually valid and that they comply to the experimental data. This can show that simulations are actually useful in predicting bioinks and parameter setup. If more information is required, one of the group members can be reached via the following email address, and the entire research paper can be found within the link. Thank you so much for listening.